So welcome to the pre-recording of lecture 14 of MCS 572. So we are introducing ourselves to supercomputing. So far, this has been a very hands-on course, mainly focused on how to get things done. In the lecture of today, we are not looking at any particular code. My goal for this lecture is to introduce concepts. How do we evaluate the performance? I will introduce three concepts. The concepts of isoefficiency, that kind of generalizes the earlier laws of Amdahl and Gustafson we encountered in lecture 1. The second concept is on task graph scheduling, to kind of identify the bottleneck in a parallel computation. So also very useful for shared memory parallel programming. And then I will end with the roofline model, where we can make the distinction between a computation that is memory bound or compute bound. Okay, I hope to explain this in 40 or 50 minutes. So far, when we look at the running of programs, we're looking at the time. So we have time metrics that come from measuring the execution time. So the execution time typically consists of CPU time, system time, but also time for input and output. And then there is the overhead caused by communication and synchronization. Often the most honest and time measurements is simply the wall clock time. That includes both the execution time and the overhead time. These are the time measurements. And in this lecture, we are now mainly concerned with derived metrics. We have time metrics directly from what we measure. So we just look at the wall clock, for example. But then we are interested in performance in floating point arithmetic. So if we think about scientific applications, we compute and we report the number of floating point operations per second. So in order to get this metric, you have to look at your code and analyze, if you have a computation, how many floating point operations that are done during the entire runtime of the program, and you have to measure the execution time and then compute this flops ratio. So this is not typically something that, well, there are tools for doing this, but typically this is something that involves a separate computation. When we introduced message passing, we were looking at the communication to computation ratio, and that's a measure for the overhead. Time here can be also expressed with the big O in function of the dimension of the problem. So if your execution time, if your running time is quadratic in the dimension, then you would like that the communication time is linear in the dimension, so that the overhead as the problem size grows actually does not start to dominate. It's pretty bad if the communication time actually grows at one order more than the execution time. And we will also be interested in the memory access to computation ratio. We look at the time spent on the memory operations. So we look at the memory bandwidth, over the execution time. So we will determine, for example, the number of operations per byte. So these are three different types of derived metrics. Okay, so this is extremely important because we want to determine the performance of parallel computation. Performance is often used to make value judgment. So is a computer good or not? So there is the peak speed. So the next week, so we are now towards the end of the parallel shared memory, parallel programming. But in the next lecture, so we still have one more lecture on this, but we will go into graphics processing units. There we can theoretically achieve teraflop performance. Another way to measure the performance of computers are using benchmark. So the top 500 supercomputing is using a Linpack benchmark. Why is performance also so important? As a software developer, you want to know when to stop optimizing or where to optimize. So if we defined tasking in earlier lectures, so one can analyze the task graph, and in particular looking at the critical path in such a task graph to kind of determine the maximum speedup that can be obtained without essentially running any program. So everything that will be discussed in this lecture will not require the running of any program. Okay, so this is the use of metrics. So let's now look at scalability and relate this to speedup and efficiency. So speedup is the metric that we have been using just as the first order of metric because it's such an easy metric to use. So you look at the ratio of serial time versus parallel time. And you hope that that goes to the number of processors. One may also achieve super linear speedup. Sometimes this could be even more than the number of processors. Then there is the efficiency metric. So we divide the speedup by the number of processors. And with an optimal speedup, the efficiency should go to 1. But what actually prevents the optimal speedup is the overhead time. So the total parallel time is the sum of the overhead. So contains, so we can define the efficiency in terms of the serial time over the parallel time. So here assuming that you have this, so the speedup is the time over parallel and the time over the serial time. So the first writing here of the rewriting of the efficiency P is using that definition. So the denominator can be P times TP is the serial time, but that includes the overhead. So in the notion of efficiency, we have the ratio of the overhead over the serial time. So we will define now scalability. So we will examine the scalability to see if the problem size grows, but also with the increasing number of processors. As the number of processors grow, can we actually keep the efficiency? Can we still have a good speed up? Okay, we will relate the efficiency to the problem size, denoted by W. So the overhead will grow with the number of processors and will grow in the workload. So there is some function now. So T underscore T subscript big O is the time function for the overhead. So we can define the parallel time now related by the work size. So the work size over defined by P is actually the time it would take, assuming a very good speed up here by P processors. You would think that the time would be divided by P, but one needs to take into account the overhead. So the speed up that then can be obtained can then be expressed in terms of the problem size, the number of processors, and the overhead. And likewise, so by using the definition of efficiency, we can rewrite the expression for the efficiency in terms of the overhead, the number of processors, and the problem size. So now if we look at the scalability, we let the number of processors grow, which is actually unrealistic. Typically you have a fixed parallel computer with a fixed number of processors, but let's, for the sake of argument, assume that we can have an unlimited number of processors. So we say that an algorithm does not scale well if the problem size must grow exponentially to keep the same efficiency. The algorithm will scale well if the size of the problem only needs to grow moderately to keep the overhead in check. So these are definitions that hopefully make sense now. It will be illustrated by examples. So here is now the derivation of the isoefficiency. So we have derived the formula for the efficiency in terms of the problem size and the number of processors. If we are rewriting this, then we can arrive at the ratio over the overhead and the problem size. So the overhead is expected to increase as the number of processors grow, but we look at the ratio of the overhead over the problem size. And it turns out that that is related, that this is equivalent to the efficiency ratio. So rewriting once more, we can express the problem size, relate the problem size and the overhead with the constant k. So we keep the same efficiency, which means that also we keep the same speed up, relating the problem size with the overhead. Okay, so this is the important concept of isoefficiency. Let's step back. So here we have the isoefficiency again. How does this relate to the earlier laws that we covered? So we covered them in lecture 1 because these concepts were very straightforward to illustrate and understand. Amdahl started from serial computation, where part of that computation had to be done sequentially, and then let the number of processors grow. And there we got to upper limit on the speed up. So in some sense, this was a very pessimistic law. But this law kept the problem size constant. Gustafson said, you know what, this is very unrealistic. You actually use a supercomputer to solve a problem that otherwise could not be solved sequentially. So you kind of compute the speed up by looking back. So you have a fixed, you have a workload, and part of that you've solved a big problem, and part of that was spent sequentially. And one can, based on that, one can compute the speed up. So these were the two laws that we have introduced fairly early on. So these were laws that were one-dimensional. So one kept the problem size fixed, the other one kept the number of processors fixed. With the isoefficiency, we can play with both parameters. So we have the number of processors and we have the problem size. And we relate them to each other by using this concept of isoefficiency. So let me illustrate this. So this is with the parallel fast Fourier transform, which is an n log n operation. So we have the isoefficiency function. So the sequential time depends on the problem size, n. It's an n log n, and then the time for complex operations. So if we look at the parallel computation, we have a startup cost that depends on the number of processors. We have also a communication cost. Here, the transfer. So the communication cost is the startup time plus the transfer time. So for the parallel computation time, we divide the serial time by the number of processors. So the overhead is written here by the communication time, startup time and transfer time. Okay, now efficiency, we work out the formulas. So we have one complicated formula there for the efficiency. Let's simplify this a little bit. Assume that we are working with shared memory and there is no transfer time. We still have a startup cost. You could say it's also the synchronization cost or the launching of the threads, probably more accurate. So we do have the TS sitting in there, which is dependent on the number of threads that we are using. So we can then compute this isoefficiency constant and compute the isoefficiency function. So there it is. So we have the workload, the problem size, W, capital W, related to the number of processors and the ratio of the startup time over the compute time. How can we work with this function? Here we evaluate this function for the number of processors with fixed constants, and we see that the problem size needs to grow linearly with the number of processors. So this is the isoefficiency function. I think that for this example here, it's just the constants are all taken to be 1. So it's just the capital W equals P times log times P. So this expresses the excuse me, it expresses the growth of the workload for having the same speed up. Kind of confirming Gustafson's law. If you're going to use 256 processors, well, your problem needs to be significantly larger than if you're working with 16 processors. Okay, this example was um, was for shared memory. Let's do the same illustration again now, where the startup costs is ignored. So now we have the ratio of the transfer cost, so the cost for one word over the communication cost. And that is also now, there's now an important difference. Now we have the n times log p comes in there. It's not the p log p anymore. So that's the important difference in this analysis. So here is the plot. So in this case, we actually look at the number of processors, and we look at the isoefficiency lines, letting n go from 10,000 to 100,000. So you can see that if you want to maintain an efficiency of, say, 70%, then your problem size needs to be increase steadily. You have this band of efficiency, although it's here actually not that bad. You still keep 60% efficiency for all problem sizes, but you actually don't get higher than 70%. So for 16 processors, you get more than 70%. You get close to 80, more than 80, a little bit over 80%. But as your number of processors increases, then actually you don't get to 70%. So this is this plot which kind of summarizes the situation for distributed memory. Okay, also these computations here are for normalized constants. Why are these plots interesting? They kind of give you a cost analysis, so kind of a prediction to motivate, to kind of justify. So you could use plots like this to justify the purchase of, say, many processor machine, or the consideration for many processors. If you have a scalable algorithm. Okay, so that was a very brief introduction to isoefficiency. Parallel algorithms can be defined by directed cyclic graphs. So these are task graphs. In some sense, we kind of introduced the concept already a little bit with the dependency analysis, with the Bernstein conditions, and with the depend clauses in OpenMP. So in a way, I try to keep the lecture self-contained. But here you could define a parallel algorithm by adding the dependency conditions from the Bernstein conditions, or when you think of OpenMP, by adding the depend clauses. So this can be done at quite a high level, giving the task graph to the scheduler. That will then decide how to map the tasks onto the threads. And with task graphs, we can actually analyze, just by looking at the critical path in a graph, we can actually predict what the optimal speedup will be. So this is a bottleneck analysis. I will illustrate this concept with a very classical algorithm, forward substitution. Here the forward substitution starts from a lower triangular system. So we start by computing the first instruction. We have one division, and we update after we have computed the x1, we update the right-hand sides. You can kind of see what the parallelism here already is. even for this example, you can do the update of the right-hand side, B2 and B3. You can do them simultaneously. So the algorithm for 3, if you understand it for 3, you can start writing the algorithm in greater generality. So this is one of the lectures, one of the exercises in numerical analysis, the algorithm for the forward substitution. So for every arithmetical operation, we identify a task. Here it's kind of interesting. The task can be indexed with a double index, and the index is actually the index I and j. So it's a double loop. We have a triangular system, and the identification of the tasks, they will correspond to the nodes in the task graph. We mentioned the Bernstein conditions. So here are the Bernstein conditions again. What we actually want is that when we can, so the Bernstein conditions impose conditions on whether we can run tasks in parallel, and they can be formulated in a very obvious manner. So the in and the out. So these are the 3 conditions. The 3 type of conditions. So for every instruction, we can list what is the in and what is the out. So what goes in and what goes out in every task. So we can formulate this quite in general. For every task, we can list the inputs and list the output. So we've seen with the OpenMP dependency clauses, we can give also the in-out. So with the tasks ij, we would have an in-out dependency on the ith component of the B vector. Okay, why is that now useful? Well, the picture actually illustrates this. So we can think about the general algorithm, but the general algorithm is actually best explained with the task graph. So we have the first instruction. So every task is blocked there for the computation of x1. Then we update B1. We update B2, B3, B4. Then we compute X2. That's the task T22. After which we can update B3 again and B4 again. Then we compute X3 before the computation of the update of B4 once more, and then we can compute X4. So the task graph illustrates the flow of the operations. So the arrows indicate also the data flow. So what goes, so the x1 goes in the first arrows. What comes out are the updated right-hand sides. Then we have again the update, the computation of the components of the solution, so the xi's. So they are computed in the diagonal task, so when the I equals j. So the labeling of the tasks here matches very nicely the logical definition of the items that are computed in by this algorithm. Okay, so why is this now so useful? So the critical part, so there are many critical parts. So I will follow the top So the critical path indicates the instructions that, so you go from the beginning to the end and you follow, so there are many critical paths, but you count the number of nodes in the critical path. So that gives you the length of the critical path. So, and you compare with the sequential execution. So you see the nodes that are in red. So there are 7 nodes. So in parallel, that means that you have 7 steps. And the sequential operation is when you sequentialize or you serialize everything, and that would take 10 nodes. So 7 over 10 is therefore, or 10 over 7 is then the speed up that you can expect. And this is a number that can be computed without doing any, just by analysis of the algorithm. So here is the analysis of the algorithm for 5. So that was the largest one that I could fit reasonably on a slide. So here you see that the length of the critical path now contains 1 node more. Or 2 nodes more, I'm sorry. So the general formula can be derived from that. For n equals 4, we found 7 as the critical path. For n equals 5, we find 9. So the formula from this, so 9 is 2 times 5 is 10 minus 1. 7 is 8 minus 1. So we actually found the length of the critical path. We conjectured the length of the critical path as 2 times n minus 1. So it also, you can also see the immediately from that, so the number of instructions that can be, the number of tasks that can be running in parallel at the same time can also be seen from this. So you can see that for a dimension 5 system, the maximum number of tasks that can operate simultaneously equals 4. And you can compute there also the speed up. So for any n, the length of the critical path is 2n minus 1. In a more mathematically oriented course, so this would be proven by induction. So this is actually an opportunity for that type of exercise. You can also compute the speed up for this. Notice that this is instruction level parallelism. For parallel linear algebra, and there will still be lectures following there, you would reason with block structures. So instead of having, you would do the forward substitution on a blocked matrix. And there would be still a lot of parallelism when you do the invert of the blocks on the diagonal. And they can be done, so you start from a block triangular matrix and you start inverting the elements on the blocks. So, but I'm running a little bit ahead of this. Okay, for now, so the metrics where I started in the introduction with are given in the Encyclopedia of Parallel Computing. The task graph is also defined in the same encyclopedia. For the isoefficiency, there are the journal papers and also the textbook. Then there is the last reference there that computes and illustrates the notion of isoefficiency on the parallel Descartes method. So I gave the example on the parallel fast Fourier transform, but the concept of isoefficiency can be done for any type of computation. Okay, so this is the recommended reading where I got my sources from. So I still have about 10-15 minutes for the last tool to evaluate parallel performance. This is the roofline model. So what we look at when we consider a problem, we can define the metric of arithmetic intensity. And this is a derived metric. We compute the number of floating point operation per byte. That is the derived from the flops. So here, when we look at the simple addition of two numbers, we have to get the operands out of memory. So these are two 64-bit doubles. We have to do the computation, so that's one floating point operation, and then we have to assign the result to another 64-bit double. So we have a total amount of 3 doubles, so we have 24 bytes, and we only do one floating point operation. So the arithmetic intensity is 1 over 24. So that is the computation of one floating point addition. It's going to be a memory-bound operation. So one can also always ask, if you purchase a computer, do you want faster memory or faster processors? So I'm doing this recording on a MacBook Air. It's the M1 processor, but I have another MacBook Air which runs at 1 gigahertz, which is actually quite low, but which still performs quite well because it has a fast memory. So because most operations are actually memory bound. So computation is memory bound if actually the speed of the memory, and that is expressed in the number of bytes per second for memory moves. So the memory bandwidth actually is going to determine the performance of a computation. On the other hand, we in scientific computing, we think about flops, and we'd often think that the peak floating point performance determines the performance. And this is only so if we have computations that have a high arithmetic intensity. So these are two things to keep in mind. So now we get to the roofline model. So I copied this picture from the paper that introduced or that described the roofline model. I heard about this for the first time at the SCIEM Parallel Computing Conference. So we have the roofline. So the peak floating point performance is the theoretical peak performance. So here on this particular example, this was 16 gigaflops per second. So that's the vertical axis. But then you can express this in the operational intensity, the horizontal axis. So they have the slanted line, and that line is determined by the peak memory bandwidth. So what is now the formula? So obviously the peak floating point performance is going to determine the upper bound, so that's the obvious upper bound. But then you have the memory bandwidth multiplied by the operational intensity. Notice the units. Peak floating point performance is always expressed in typically gigaflops per second. Memory bandwidth is the number of bytes per second the operational intensity, and now I have to flip back here, is the flops per byte. So you see that if you have the units, peak memory bandwidth, flops bytes per second, but then there you have the operational intensity flops per byte. So the byte actually from the operational intensity in the denominator cancels out with the numerator in the peak memory bandwidth. So the units actually fit. So that's the formula also to compute the ridge point in this roof. Notice here the difference between the arithmetic intensity and the operational intensity. So the operational intensity measures the number of operations per byte. In scientific computing, we tend to focus on the floating point operations only, but that leaves us a little bit at an odds when we talk about parallel sorts. I mean, if you do a parallel sort, you don't actually do any floating point operations. And you still want to say something about the performance. So that's why the operational intensity is often preferred over arithmetic intensity. So here I'm actually commingling them a little bit. Okay, how do you apply now the roofline model? Well, you look at the specifications of your computer and you read of the theoretical peak performance. And that are the theoretical gigaflops per second actually gives you the units of the vertical axis as well. So that's this horizontal line. Then the ridge point will tell you, will actually, you can compute this as well. So you know, you read of the specifications, the peak memory bandwidth, and you compute this ratio that will give you where the slanted part starts. So for any particular computation, you know your arithmetic intensity. So here I'm again working with scientific computing in mind. So you know how many floating point operations that you have done during your computation. So that gives you the performance. So this you know the y, but then also for any computation you can analyze the arithmetic intensity. So how many floating point operations per byte did you do? So the number flops here. So flops per second is kind of I'm not using flops also consistently. Flops often is set as the unit for speed, but flops is also the count, the number of floating point operations. Okay, but the neat part is that for any computation that you do, you have a dot that you can place on the under the roof. Okay, so now I illustrate this with a picture that I took from a tutorial. So here we have the red horizontal line, which is the theoretical peak performance. And then we have the slanted line, which is the memory bandwidth, and you see the ridge point. So with the black dot, you see the computation that was done. So the x and the y, they gave you the coordinates. And then you can see if you're under the slanted part or if you're under on the horizontal part with your dot. If you, and under the ridge point of the roof will actually make the cut between whether your computation is bandwidth bound, memory bound as well, or compute bound. This is another way to actually examine the scalability. So this is one point for one particular problem size, for one particular number of threads. As you increase your problem size, you would hope that your dot moves up and that your dot moves to the right. So This is so the higher the dot, the better. The better you are examining the better you are exploiting the capabilities of your computer. So this is a very important conceptual tool to examine the type of your computation. And there are also tools that will help you determine making these plots. So if you have a run of a computation, whether your computation is memory bound, whether you actually would benefit from faster memory, or whether your computation is compute bound, whether you can really utilize the fast processors and the many cores on your processor. All right. So there are many concepts that we have examined here. So there is the isoefficiency formulas. So you can make plots for very specific values for the transfer cost, the startup cost, and the computation cost. One can make plots like this, even without doing any computations. For the forward substitution example, you can apply the Bernstein conditions and verify the correctness of the code as well. So match essentially the directed acyclic graph with the Bernstein condition. So in some sense, I jumped a little bit too fast between the derivation of the task graph and the Bernstein condition. So what the second exercise actually asks for is to justify the directed acyclic graph. Okay, so I'm very close to the upper limit here of what I allowed myself, the 50-minute window. There are many useful concepts to evaluate the parallel performance, the isoefficiency, the critical path analysis in a task graph, and the roofline model based on derived metrics. So later in the course, we will refer back to this lecture when we will see many more illustrations on how to evaluate the performance of parallel algorithms and implementations.